So I'm Matt Ingenthron from Couchbase. This is my colleague Dustin Sallings. We're going to break this up a little bit. So I'm up first.
Oh, no, go ahead. You go right ahead.
So I don't know how many people are aware. Just to, I'll kind of walk through it a little bit. So Couchbase, we're really kind of a combination of a number of the people that had been working on Apache CouchDB, and then we had another project that Dustin and I were working on that was called Membase. We brought this together a little over a year ago, and we've been shipping some things since then. So, by the way, can everyone hear me in the back? I don't have a mic on. Okay, cool. So who are we? We're the makers of a high-performance document database. So am I supposed to be controlling it from that? Right?
No, you can.
Okay.
You can
see what's next. I see. So we built a database that's sort of in that NoSQL category, and there are a lot of different ways that you could sort of break up NoSQL, a lot of different ways that you can look at it. So more realistically, what are we? We're a distributed. We're a database in a more specific way in that NoSQL category. We're distributed across many systems, many VMs, designed to scale quickly. Designed, and this is actually where we've leveraged a lot of Erlang, specifically Erlang OTP, designed so that we don't have any special nodes within the cluster, nothing special that you have to have. I won't go into lots of theory on things like CAP and so forth, but by design, Couchbase is consistent, and we think that that was the right approach for the kinds of applications that we're building for. By design, we have a managed cache as part of Couchbase. So we very carefully look at how we manage system resources. We very carefully look at how we can get the information people need who are operating applications to be able to understand, to do capacity planning, things of that nature. A lot of that was driven by some of our early deployments, is that we just ran into these issues early on, so we needed to be able to get a lot of info. And that's actually where Erlang's worked very well for us, is we have this I always use it as sort of this, we have this control plane layer that we use within Erlang to understand as we build out the cluster and understand what's happening within the system. And we've built all of that clustering. Who uses it? That might be another way to talk about where does it fit in the NoSQL continuum, or whatever term you want to use. So just a couple examples. Ad targeting. This was. Wow.
Someone targeted that ad.
Speaking of ad targeting, the ad targeting was actually not a use case that we anticipated early on, but it turns out, and I don't know if anybody in the room does ad targeting. I'm going to give a really pedestrian definition. You have to display a little, advertisement, and you have about, typically, from one of our customers, about 40 milliseconds to come up with that answer to display it. So the faster that you can get that, the more time you can spend on all of your logic on which is the right ad. So because we were super fast, because we had a good way to grow these things, people like AOL advertising used us. Social gaming was another one. This was partially, Zynga was one of the original co-founders of one of the forks of the projects, Membase. We started doing a lot of work with Zynga early on, and then just last week, actually, we had a kind of a little success story that we were able to talk about a few weeks before that. I think about a month before that, actually. A company named OMG Pop, who have a game named Draw Something. So Draw Something they'd put it together and they deployed it on Couchbase, and then it went viral. So it's been out there and deployed across lots and lots of. We should invert these or something.
No.
So it went viral, and now it's been, I can't remember the number of users, but they just had to continue growing and growing the cluster. And the good part is that with the clustering that we built on top of Erlang OTP, we were able to just continue adding systems to the cluster and continue growing it out, still continue to add people.
So since there's kind of this vague sort of view of it might be worth mentioning that the clustering that we use is very much the OTP clustering, and we use the OTP supervisors throughout the application with some small differences. The thing that we're doing for the really small response times, we actually had a customer who was asking us for a 100 microsecond SLA. they said they were getting that most of the time, but they wanted to make sure they never got that below 100 microseconds on the 95th percentile. We do that with dedicated processes that are, crazy tight C code that shouldn't, exist in this modern age. And those are an extension of OTP's concepts of supervision, in that we've built these supervisors to run those specific processes, so they act very much like any other process that would be inside the Erlang system, but they're external from that.
Correct. Actually, my presentation at Erlang Factory last year went through some of that and some of the things that we built for that.
Oh, so just watch that one.
This year we're talking about tracing. The other example of deployments, things like all recipes, Concur, who do travel monitoring, lots of situations where people have social apps and content that are kind of combined together. Just a couple things. I actually think this is pretty cool, but part of the reason I think it's cool is because I was pretty involved in at least the first version of it. So we use this UI is actually really just jQuery making calls into Erlang through MokiWeb, and so it's really just any node in the cluster can serve up this UI, and it's really just a matter of going and asking the cluster for different kinds of statistics from the overall cluster, and then the browser does the rest. So it's just, to overload the term,
literally, the browser does the rest.
Browser is receiving these REST responses and then rendering it. So what you would see if you're running a cluster is you would see a set of nodes that are out there running within the cluster, and you can drill into what's happening with them. And it's even as simple as if you want to add another one, boot it up, install the package, hit the add server, go tell it where the IP is, and under the covers, we do all the OTP ping pong to get everything worked out between the two nodes. So the user's abstracted away from all that. They don't have to set up any config files or anything like that. It all happens through the UI.
Yeah, randomly generated cookies and all that kind of stuff.
Yep. So as I mentioned earlier, we spent a lot of time thinking about how we can get the kinds of metrics we need out of the cluster to be able to run this system and understand what we need to do for capacity planning, be able to operate it in a really large environment, and an environment that's scaling really fast. So this is just one example where we actually use the Erlang cluster layer to go out and understand the processes that we're managing under a set of supervisors. We'll get statistics out of them, pull that together, do whatever aggregation we need to do. We actually keep it for history. We do sort of an RRD, round-robin database, where you lose resolution as you go back in history, because 2 weeks from now you don't care about what happened between second 34 and 35. So we do things like that where we'll keep the history, and then we have just a huge number of kind of metrics to be able to understand what's happening with the system, and that way people who deploy it are able to plan accordingly, see how a new application push affects the way the database is deployed, things of that nature. So with that, I want to turn it over to Dustin, who's going to talk a little bit about some of the problems that we've run into and the way we've handled them, which addresses kind of this DevOps track. Okay, we're developers, we have these operational issues, what do we need to do to try to understand them?
So the interesting sort of thing that happened as we transitioned into the sort of thing that we described earlier to what we were doing with CouchDB is that historically these processes that were really insanely optimized C code, we're dealing with all of the I/O on network and disk and all sorts of resource management, and Erlang was basically OTP as a service that we could spread across all kinds of things and benefit from. Then we started adding a lot of features that we inherited from CouchDB and started bringing that into the management layer. And that's where we started running into these issues where some things weren't meeting our performance expectations as they were. And the general response, I'm sure all of you have seen this before, is we'd have a lot of developers who we'd go back to and say, this isn't fast enough. It should be at least 2, 10, whatever times faster for this type of operation. What's your estimate on how you'll be able to get it to go faster? What's the problem analysis and all that kind of stuff? And the response that I get back, which is literally this is a response I got back from some of our core developers on Erlang, is I don't know. They just scream, it's Erlang, who knows, it could be anything, we can't tell what's going on in the box, it's just magic, and if it doesn't work, we need to rewrite everything in C. And I'd sit through tons of meetings of like, if anything's wrong, we have to rewrite it in C because it's Erlang, we don't know what's going on. Of course, that's really frustrating for me because I'm like, we know what's going on, we have data, we have tools, and if you are just telling me that you don't know what's going on, then that's kind of your problem, and I need to get someone else to do the stuff. So that ended up being me. And I like to look at actual data and say, what can we get out of the system? It is fundamentally, if you tell me that you can make this work in C and you can't make it work in Erlang, I will tell you that the Erlang VM is written in C. And if you can't extrapolate from there, then you're just kind of in my way. So the first thing we did was we started looking at some of the stuff that we could get from Erlang. So Fprof, we had someone run tracing, ran through Fprof, and I got this, right? So first pass on Fprof was actually I got 60 megs of this, and the guy just came back and said, well, you figure it out. All I got was this giant text file. So I took 60 megs of text file and said, okay, I'm a programmer, I can program. So this thing is kind of self-describing. It's fairly well documented. I can kind of figure out what's going on for that. So I built a tool that could eat all of that and spit out this. So this was pretty helpful. I have a bunch of these things. They're big, giant, complex pictures. And they would draw these little red boxes with red arrows saying, this is sort of where most of the time was spent in this area. And I could say, well, this stats aggregator would occasionally go completely insane and start eating lots of CPU. And we can start looking at that. But the general result of that wasn't terribly useful.
Before you go forward on that one, notice that the big boxes are like 2%.
Yes, right. So what we'd get is a whole lot of like 2% and sometimes a 5%. And you kind of look at that and go, well, I mean, I like to ignore Amdahl because there's another guy in the company who's always saying his name, so I'm going to fight him. But yeah, we're not going to get very far kind of targeting that, but at the very least, we have something that we can kind of look at, and we can start following kind of the things down. So, but we did start looking into other tools because there's other tracing stuff, right? It's not just Fprof, but it's hard. And I actually didn't draw this way. It's really funny. It decided to just throw them all in a big pile that's useless because that's kind of what I experienced. There's all these tools that can do various types of tracing. And every one of them that I would find would have like a DSL for defining trace points and all this kind of stuff. And they would all say, but if you do something wrong, you'll deadlock the VM. And if you do something right, it'll just run too slowly for me to actually run my tests. So I could kind of get an idea of particular bits of code taking too much time. But what I couldn't do was say, what is this system that's running, spending its time on without stopping it from running or having more information than I could actually log to work with. And then even if I got that working, there's still this stuff I don't know, because one of the first things that we got was, well, it looks like we've got some memory pressure because we have competing processes on this box, like actual OS processes that appear to be suffering memory pressure, because one of the things that is fairly highly optimized C starts to slow down quite a bit when Erlang starts to kick in, and we have available CPU, but it's not kind of using it very well. So we're trying to figure out how these two things that are otherwise independent are affecting each other. Also, just like some simple stuff that's kind of hard to trace. I mean, you kind of do it with the tracing, like scheduling events, but then you get into like OS and device interactions. I can ask questions, for other parts of my system, like when am I, actually touching this device driver code, because I want to know when I'm actually doing real IOPS, not just doing write syscalls or something. And some of those are surprising because you get them from like swapping or whatever. There's internal messaging, cross-node messaging, various things that you can kind of do, but not in a sort of holistic way on a running system without being excessively invasive. So this, of course, going back to the developers, meant that they say, aha, I have an excuse again. You can't answer any of these questions. So that's when I started, fine, I use Detrace for all the rest of the stuff I'm doing. Let's get Detrace into Erlang. And it sounds kind of like, yeah, we've got this giant list of tracing tools. Why do we want more? We already have tracing. This doesn't seem like the kind of thing that would be terribly beneficial. But the thing to understand, and this is this is really hard for anyone who's not actually used it, is a Detrace script is not something that you place into your program. It's not strace, it's not any of those sort of things. It's an actual script that your kernel runs. So your program is the entire operating system that you're working with. And it sees everything from like little tiny user probes that you decide to place in your application that say, I have started this event, I have ended this event, all the way down to device drivers and lines of kernel code if you really want it. So I can go literally from tell me the function that is running when this SCSI device kicks in or something bizarre like that. So it's very, very far-reaching, but also when you have your kernel as the scripting language, a thread has no sort of distinction across processes, for example. So I can trace things that are coming in through my little C program and then feeding data into Erlang and where it goes into Erlang before it comes back out to the C program. I can see the entire world. So it seemed like it was worth the effort to kind of get in there. Although, there's still the question, what's the point? And it is that my program is more than what's running in the Erlang VM. In particular, it's how it's affecting the operating system and as much, like very simple things, like this is one of these where, the other way to do this would be just pull up a terminal and just have people ask questions and go, because I can say, which CPUs are not getting scheduled, how is my SMP laying out across CPUs, anything like that I want to do. But there's very specific Erlang stuff I wanted to get in so I could understand what's happening in the VM a little bit better. So the function entry and exit, that's really common stuff. I want to know when a function starts, when a function ends. Bif and nif are actually really simple. Functions are kind of hard because conceptually, when does a function get entered and when does it get exited in a system that's like has mutual tail recursion on the the VM? It's really, really hard. But when we're looking at like memory pressure, there's object copies, which are completely without context. A function might cause an object copy either by doing a message send or allocating one or something, but the object copy occurs without context, and that's where we start to get into memory pressure. So when am I moving a lot of data around in memory that would be affecting other parts of the system? Processes starting and ending. Lots of stuff that you can see on your Unix system happening here. I want to see it in here, and I want to see it in context with the rest of the system. But in addition to the stuff that I'm getting that's Erlang specific, I want to see the rest of the system. So I want to know what's triggering heap expansion. So Erlang occasionally has to go to the operating system and ask for memory and get it back. When am I doing that? What's causing that? Which exact thing is causing it to actually grow the heap? What's causing actual IOPS? Am I using the file system cache effectively? That's a big thing that we have. We've got this append-only B tree that we're writing to disk. Theoretically, the head of the B tree stays hot. In practice, does it? I can tell because if I'm doing read and write syscalls and they're not actually leading to IOPS through the device driver, then I know that the file system's taking care of cushioning all that for me. But if I see every one of those reads and writes actually causing an IOP, then I know that I'm not actually using the file system cache effectively. And most importantly, I know this on the system while it's running. I don't have to take it apart, do instrumentation, put it back, and do all this other kind of stuff. And just from my Mac here, when I was typing this line, there's 239,446 points that I can trace. Each one of these has context. A lot of them are things like read enter with this file descriptor, this buffer, this size, so I can say this read is beginning, it's going to move this much data across this file descriptor. I can watch it open the file descriptor so I know if it's network or file or whatever. I know when it completes that read syscall. I can take the nanosecond time between them. I know whether it succeeded or failed. I know how big writes are when they fail. I know how much writes, all that kind of stuff, and 250,000 other things. So it seemed like a pretty good thing. Matt is the expert in this, so I'll let him describe kind of more of how to use it. I just made it work.
I don't know, historically expert. So I know I think we're moving like super, super fast. We've taken 10 minutes. And
I just had a whole lot of tea.
Yeah, so we've gone through a whole bunch of material, so I may actually pause for a second and see, was that reasonably comprehended? Do you understand at least the problem domain? And we'll give some examples. Any questions at this point? Yeah.
I was wondering how much of, when you're using Fpro, since it has a really high impact on, a high overhead when it's taking the measurements, were you trying to do any of those in production, or was it only like in a lab environment?
No, this is totally lab, and this is one of the big differences in Detrace. The success of Detrace is I am on your production system already fully instrumented for everything when you need it, and then you get the razor thing you're looking for, and you can do it interactively. So there is no overhead, there is no like needing to change something until you actually start firing probes, and then you're fairly limited in the overhead that you can introduce at those probe fires. So you may see impact to some degree, but you can be very specific about it. For example, if I'm looking at IOPS, I can say, I only want to know IOPS if I'm in the middle of a function, of this particular function. So if I start the append to B tree function, then I want to track the IOPS and accumulate it back to that until it completes and then stop tracking the IOPS. So you can be very, very precise, and you can do that on your production system.
Yeah, and it's not necessarily clear from, if you see some of the details of how Detrace is implemented, you'll do sometimes like the copy instir. The reason you do that is that sometimes there's information you want to grab in a context, and when you're writing the script, it looks like it's all happening whenever that interceptor happens, but realistically it's grabbing some variables and then in its own context sometime later it's dealing with the rest of the aggregation work. The other thing worth mentioning with Detrace is there's a dead man switch, sort of. So Detrace determines that it's creating too much impact, changing timings on the system, it'll kill itself. Now you can override that. You can go back and say, no, I really do want the data. But it's intended for that. Just brief background. So it came from, and I suspect a lot of people know this, but there are probably a couple that don't. It really came from Solaris, built for Solaris 10. And at the time I was at Sun, I wasn't part of the Solaris organization, but I know people who'd worked on it. And the problem they were trying to solve is they'd already built a lot of observation tools. And we had really good modular debuggers and things of that nature to be able to understand what was happening. But you'd still have these problems. Actually, it goes back to what was mentioned this morning. You'd still have these problems like, I'm a financial services company, and every 6 months, this Unix mainframe-like thing will halt. So I want you to send a kernel engineer to sit in the data center and wait until it halts again so that they can go through debugging so that we can spend 20 minutes and understand what's happening before we send information back. And so the Solaris team sort of recognized that they needed to build the next level of tools to be able to go understand that next level of problems. All the really basic bugs in Solaris up to that point had basically been solved and needed another set of tools. Well,
and that's living today at Joyent. Those guys are still doing that. They had a bug recently where they would find that systems would continually get slower over time at something related to TCP that they'd never seen before. They went out there for a couple minutes just sort of poking around with Detrace, like, what's this, where's it spending its time, built this, this beautiful flame graph thing. You should see some of these things. And then said, oh, there's this piece in the kernel that cleans up connections after they die, and it kicks in when it's a small hash table that ends up being 256 arrays with chains off the end, and the chains are getting really, really long because nothing's pruning them, because it kicks in on a memory condition, which we don't have because we put entirely too much memory in the box for what it's doing. So they just kind of they spend 15 minutes on this and go, this is why we've never seen this before, got a kernel fix and throw it in place. Yeah. And they couldn't reproduce it on other systems because it pretty much had to be in production for a month before it ever occurred. Now they can just go, oh, it's right there, clean it up, move on.
So, any other questions? Cool, okay, move forward. So where do you start? Usually, not with Detrace actually, so you usually start by having some sort of question. The reason I always try to state this is the other tracing tools and even OS level tracing tools are usually the place that you will frequently start. So you'll start off maybe with something like an IOStat or something like that, and you'll have an interesting question. So you know what the system's doing. You might be able to see what's happening with processes and CPU time. and you know what the behavior is, but you don't necessarily know what's causing that behavior. You know what since you know what the application is doing, you can kind of look at the starting point, you know what the behavior is, and maybe it's a slow I/O, for instance, and then you want to be able to correlate those two. So that's usually where you go into the system a little further and you have a question. For example, in one case...
This is actually where your analogy fits pretty well, too.
Oh, yeah. So there's, I have a colleague who would always talk about it as, so let me just toss it to the room. What's the best debugging tool?
Print.
Huh?
Print.
Exactly. Yeah. Trace statements, right? Throw trace statements into whatever it is. So printing out. So the cool thing is with Detrace, you can basically insert a printf into a running process or into the kernel associated with a running process at any point in time dynamically.
Even on conditions.
Even on conditions, because frequently with like a printf, right, you potentially end up in this situation like we were talking about earlier, where you have the 60 megabyte file, now I got to go troll through it. I really want a conditional printf. And so usually with Detrace, you'll end up in this situation where you insert these trace statements and then you start iterating. So you do it the first time and you see, that really doesn't tell me what I want. I really want to see what's happening in this narrow range. So I'm going to add some predicates to it, and then from there I'll be able to work things out. So one example is who's copying stuff. By the way, huge props to the Bashful guys who had been doing some of this work originally. Then Dustin went back and added on to it. This code is in the current OTP code base. But we'll talk more about that.
Actually did kind of separate thing. I have a thanks at the end for that specifically. I'll just save that for the end.
But I don't want you to think that this is all stuff we've done. So we're working within the community. It's cool that a bunch of other people have been working on this as well. So this is a D script. This is a really basic D script, and I'm going to walk through it briefly. If you're at all familiar with awk, at least to me, it always reminds me of awk. So you have these things that, like, when processing, this thing's going to run, right? So when I get a line that matches. Here we're defining a variable that we're going to use later. And we're saying within Erlang, and we can use a wildcard. So in this case, we're saying all processes.
Well, I think it's important to point out that that's a thread local.
Yeah, well, I am later.
Okay.
Actually get to assigning it. This will actually trace across all Erlang processes running on the given system. And I could narrow it down to a particular PID. We've got another example of that later. And basically what we're saying is anytime we do a function entry, function return, or process schedule, any of those within Erlang, what we want to do is set a thread local variable. And we're going to copy into the string arg1, and arg1 is the function name in that case.
Yeah, it's the MFA.
Yeah. So the MFA is going to get copied into a thread local. And so that's going to become important because we're going to want to only fire additional probes later based on that thread local. So again, the question we're trying to answer is who's copying stuff. So then we can look into the Erlang VM and we can say, okay, whenever copy struct fires, if that thread local is not an empty string, I want to keep track of that information. I want to put that somewhere. So this thing here with the @ symbol is a Detrace aggregation.
That means magic.
So that means that within this running D script, we're going to start collecting data, and we're going to put that data together, and then we're going to print it out at some point later. We just named it copies, and all we're putting into copies is this same thread local, self-current, the MFA that we captured earlier. So when the process was, when we did function entry or function return or process schedule, we copied that into a variable. Later, we're sticking that into an aggregation. Within that aggregation, we're now going to do a summation of the number of times that thing is called.
So no, that's actually the amount of data copied.
Oh, sorry, you're right. Yeah, arg0. Some of this goes, but sometimes you actually have to read a little bit of C code or understand it, or
documentation,
understand what the individual arguments are. So when it gets into copy struct, arg0 to copy struct is the amount of data copied.
So the one thing that I want to point out, because it's completely amazing to the point of not being obvious, is this @copies thing is a global variable at the extreme. It's a global variable across all processes on your computer. And if you're running a jail system, that's across all sub-operating systems and everything else. So it's as global as a variable can possibly be. Whereas this is a thread local. That means if you have like 300 Erlang VMs running with, each with 3,000 processes, every time a particular function is called with an exact, signature, we add that to the global. So when we go and print out the results from that, it's really that function across everything. And that's just how this particular script's written. But that allows us to say, all the stuff running on my machine, this is the thing that's moving the most data.
Yep. And you could certainly go into like syscall type things, and you could just answer individual questions like who's allocating memory, how much memory are they allocating, stuff like that. In this case, we're digging into Erlang. The other one to show here is that there are a set of built-ins. In this case, we're using tick for a really boring thing. But the other cool one is actually there are things like the profile provider. So you can do things like run on a regular basis and do certain kinds of profiling. So some of the built-in providers, this is the tick provider, and all we're saying is every 10 seconds fire this. And all we do in that one is we're going to, is that truncate actually?
Yeah, truncate, take
truncate,
the 25 biggest.
Yeah, we're going to get the 25 biggest and we're going to print that out. So what does that actually end up looking like? Well, so when you start it off, it's going to say, oh, there are 7 probes of the 200 and, what was it, 239,000?
It's like 250,000 something.
Yeah, 239,000 probes in the system. The ones that you've requested are these 7, so instruments for those 7. And then it's going to give, you will see that the tick ran on CPU 2, and then we'll see the individual MFAs that are called along with the amount of data in the 25 biggest. So now we can see that the one that's largest is gen do call.
Do call, yeah, we got to get rid of gen. That's killing us. This isn't useful production data. This was me last night going, oh, I want a screenshot of this running. So this is whatever my computer was doing at the time, which apparently was replicating data in CouchDB.
Yeah. So, it just imagine in some other way of being able to get that data every 10 seconds on a regular basis. It'd be really hard to do that kind of instrumentation. Another question. So you start with different questions. This one came from a developer inside Couchbase.
The Kirk one from before. This is one of the things this was an assertion. You can't know this, and that's why I can't make this go faster and have to rewrite it in C.
Yeah, so the question was, how long does it take for a message to be received? And that's because so many things are happening with the message outside the individual function in Erlang. So the way, this one is kind of neat because it's not actually a script. So I know this is looks pretty terse, but it does actually, you do find after you use it for a little bit, much like you would use awk, that you can kind of just play with these on the command line and sort of iterate that.
Probably should have put a command line in there, because that was the, you can't do this, and then
yeah, and then it's start off like, well, let me see if I can do this. And so really what it came down to in this particular case, we'll walk through this briefly. What we have is we have we're the Detrace command line and a couple probes, the send, and then we have a process scheduled.
And you have to just know what the arguments are again. So arg0 is sender, arg1 is recipient.
Yep, and what we're doing is we're gathering the current timestamp and putting that into an aggregation. And at some point later, we take the timestamp and figure out when it was sent, put that into an aggregation.
So the actual thing that this is saying is how long, because I didn't have one for when a message was received, so this is sort of what we had to go with. So this is, what is the time difference between when a message is sent from one process to another and that process gets scheduled onto a CPU?
Yeah, because
that's what I had.
We don't actually know receive. So there is probably a little bit of slop in there, but it's enough to know that the process was scheduled.
But we learned from the previous talk that send is 40 times slower than receive, so this should be approximately the answer.
So I should probably call out, with the aggregations, you'll do this quantize, and quantize is either, quantize without an L in front of it is powers of 2 quantization, so that way it's really easy to just kind of see what buckets things fall into. You can do linear quantization as well, and you can play with a different quantization. But this is a command line, let me find out what's going on in this particular case. And as you can't see, if you were to walk up here, what you would see is that there are a few.
If you walk up here, actually.
Yeah, there's a few that came up that are actually negative, which is probably, we're not sure if that's a bug in
OS 10's multi-core stuff.
Something like that, but it's probably a little bit of slop there where the time slipped.
It's like negative 512 nanoseconds once.
But we can kind of ignore most of that, and we can see that right here, this is 8192. This is basically 8K, 16K. So these are the different quantizations, powers of 2 quantizations. So now we know, how much time is it taking for a message to be sent? Well, on average, 8 millis, I think, or is it?
Yeah, 8,000 nanoseconds.
I think it's 8. Don't remember the exact value, but and then you can even take that quantization if you want to do your own printf, something like that. Make it a little prettier, you can do that sort of thing. That's just an example of, got a question? Let me go see if I can work out what the answer to that question is. And with a little bit of iteration, you can get there pretty quickly. Another question, is anything allocating currently inside the system? So to look at another example, we have another thread local we're going to declare up front. Again, this is probably a copy and paste from the previous script and modification.
Yeah, plus that one thing.
Yeah. In this particular case, you'll see it's taking this $1, that's the PID. So even though we're looking across all PIDs, we're inserting this predicate and say, well, we only.
That's right. I could have done that a different way.
Yeah, it could have been up here, but anyway, the idea is that we're going to track based on the PID. We're going to take that current and we're going to copy insert arc1. Here is again the MFA.
So I can get into why this copy and paste happens a lot, but it really comes down to it's really difficult to tell because Erlang doesn't use the C stack what the current function is. So what this allows me to do is set a thread local that says what the current function was. So like the last function I'm in, because I'm going to go off somewhere else and do something. So what function am I doing this on behalf of? So when it's like copy struct doesn't have any concept of Erlang processes near it, but it happens a lot on behalf of an Erlang process. So when this process calls a function and then does a send or whatever from inside of that, that would cause a copy struct and go. Or in this case, I actually pulled out this thing called lecRegion just from one of my 250,000 probes. And that's what we're looking for. So this is exactly the printf example.
Yeah, and in this case, you'll notice that it's actually doing lecRegion. So this probe is firing anytime something has lecRegion in it across all processes on the system. But because we have this predicate in here that's checking to see if self-current is set,
it's across all providers. I always have to look up what these things are.
Yeah,
but
provider or
well, this one has a PID because
yeah.
that's a user space probe.
Well, but that's coming from that user space provider. But there could be things that are like syscalls and so forth that live in there. Without getting into a lot of detail, there is a good structured way of that falling out. The other thing that I pointed this out earlier, that Dustin didn't do, but could have done, is this actually could have been alloc splat, and then you could say across anything that starts with alloc. I want to go ahead and fire that, and then you just fall into checking to see if that thread local is set, and then you can decide if it's not set, then it's apparently not important because it was not Erlang and we hadn't been there before. So all the other allocs just go right past on all the other processes.
Or if I started the probe and it was in the middle of a function, I can't know what its name was, so I don't really care about hearing it allocate.
Yep. And so the way you would normally run this script, you'd give it an argument, which is the process that you want to look at. And you would see as a result in this particular case, allocating near, going back really quickly just to make it a little more clear, we were printing out allocating near, and then we're going to print out what the heck it is.
I didn't do quiet, so
yeah.
So you get junk, and then the
then you get what was in the specific printf. So back to what we were talking about earlier. If you can stick a printf in it, and in this case we stuck a printf in it not by compiling a beam and shoving a beam in or anything like that, but just by telling the system I want to do something.
Well, the interesting thing is I put a printf in szone malloc should clear lecRegion, which is something OS 10 internal-ish. I don't actually know what it is, but there's my printf.
Yep.
And it's because of that Erlang function that I called.
So just a quick example there. Oh, really? Oh, we sucked up a whole bunch more time. Okay.
Yeah, we sucked a bunch.
So just to give a couple, I'm going to turn this over to Dustin. He's got a couple other quick.
Yeah, so there's other non-printf-y things. The really fun thing about this one is I didn't make it. This is I handed off to one of our developers who was trying to find some performance bottlenecks and stuff. And he built this thing, and unfortunately there's a source code in one of these little things I can't quite click on, but you can build, this is instruments with OS 10 in case anyone hasn't played with it. It has a bunch of built-in things. You cannot read this at all, but so there's like basic CPU counters, so you can see CPU utilization across the top, but then you can also drop in a DTrace provider. And in particular, he had one that was looking at read and write syscalls, and another that was looking at Erlang function and tracking that. So what it's showing here, I could pretty much say anything. No one will be able to confirm or deny. But here's like you see reads and writes occurring at the level of the provider that came with instruments. And here you see the Erlang PID. Well, I don't know why I say C, you don't see that. But here's an Erlang PID and the function that is leading to those reads and writes. And then you can see the increased volume here, and he can track that down and say what's happening differently across these sort of things. So he just kind of threw that together and said, hey, look what I did with that thing. So it's cool if people are kind of looking at stuff. This is one of those flame graphs that I was talking about. This is not Erlang, but it so could be. And this is really quite nice. So this is about what you'd expect on a profiling tool, right? I've taken this window from here to here, this sort of time slot. And then these are stacks of functions that are kind of coming out of that. The really fun thing about this one is it's Node.js. Okay, that's not the fun part. But the fun part is that like you see a really clear boundary where this line right here is illegible. It tells me the name of the JavaScript file, the line in that file, and the function name that's being invoked before hopping into libpng, which hops into libz. And then you can go back and say, well, clearly this thing is where I'm spending a bunch of my time and sort of track that down. And just dropping these things out is, this is the type of thing that they use to find that kernel bug and stuff. And so just
x-axis is wall clock time. Y-axis is the stack.
Yeah.
I remember from certain ones we would, where we'd put together these visualizations, you'd see things like, you'd see this little thing that's doing this, and you'd go back and look and say, oh yeah, look, somebody's walking a hash map.
Yeah. So the tallest thing that you find that's wide, just go fix that. Wow, I just skipped right over that. Ignore that. So yes, Detrace everything. This is a particularly fun one. Brittany Gregg is amazing magician. This is a graph that he did detracing Joyent. That's all of it. Or that's one of their data centers. So those big blue bubbles there are people who need to pay them more. So they can really trace down exactly everything, which is awesome. Everyone should trace everything all the time. Except we have this problem. A lot of our customers run Linux, mostly the ones who have problems and ask me to go look at them. And this is the issue, right? So Oracle announced, yes, we have Detrace. Adam Leventhal said, no, you don't. If you do the Detrace list of probes thing, it tells you have 574. I have 250,000 on my Mac. This is not useful. There's not enough parts there. And this is after you buy Oracle Linux, who actually kind of own all that stuff. If you're on a non-Oracle Linux, you're just kind of screwed. But no problem, there's system tap, right? It's actually really cool. It's compatible with Detrace. They actually have a command line tool called Detrace. And it spits out the right kinds of probe stuff and does all the right junk to get your user probes into your application. So getting Erlang's probes building on a system with system tap was actually pretty straightforward. I don't know anyone who's made it work. It's It's horrible, and it's amazing because I've actually talked to people who care about that sort of thing. I'm like, why is this terrible? Why won't they fix it? And they have good reasons. They're basically DTrace started with an API and said we'll build to this. SystemTap started with we'll just give you all the symbols in the kernel, and the kernel developers are like, that's not an API. You can't do that, so they won't take it, and you get all these sort of issues from there. Rushing through, it's like, I have anything that's not Linux, so everything's cool. Except last night I found that the current master branch is broken. If you try to turn on Detrace stuff, you don't get build work. And all that really means is CI would be great, because whoever's doing builds is not actually running that code through their compilers, and someone's changed an API and now nothing compiles.
That's okay.
A lot of times I'm talking actually faster than normal. This is great. You guys must love this. But we do this, and we solve a lot of our problems by not having them happen on Linux, and then reproduce them somewhere kind of more sane, and then the solution sort of applies over to Linux. It would be great to be amazed by Detrace and let people know, so that we can actually kind of keep it alive.
To everyone else, Dustin's done some work, Bashful's done some work. If this is at all interesting to you, we'd love to get you involved in it. So let us know. So I just figured one way is send a tweet or something. The other thing is, let's try to figure out how to build maybe this Detrace stuff in OTP more regularly, so that it doesn't end up getting broken. And then finally, meta probing, things like function end. There are some things that we've been pretty pragmatic about what we needed to add.
Yeah, we added stuff we needed. Bashful added stuff they needed. Actually, then Bashful, Scott over there, this is my sort of thing section. He really took over the work and really kind of pushed it forward. I did the thing in a couple days that solved my problem, sort of, or at least pointed out that my problem wasn't going to be solved that way. Because people were like, no, I still don't know, even though you told me. So he really took that work and got it together and got it into Erlang proper. We just need to get people to compile it now. And Brendan Gregg is the guy who made a lot of those really amazing tools, and Adam Leventhal kept me from having to download Oracle Linux. So that's much more time than we have.
Thank you all. Thanks.
Yeah, find us somewhere else.